Hello everyone. In the last lecture, we had looked into different methods of arrangement of electrodes for carrying out resistivity survey. Here is a comparison showing you the advantages and disadvantages of the methods which we have seen in the previous lecture. Right. So, if you look at the first case, that is the Venner method, right? What are all the advantages? It is easy to calculate the rho A value. Why? The value of rho A is dependent on what is known as resistance measured as well as the constant K, which is dependent on the way in which we arrange our electrodes. In the case of Venner method, it is easy to calculate K. K in the case of Venner method is only equivalent to 2 pi times of A, where A is the distance between the electrodes. So, it is easy. And second major advantage is less sensitive equipment itself is necessary. There are number of manufacturers who sell resistivity meters. A simple resistivity meter, cost effective or low cost equipment itself will be sufficient to carry out the survey using Venner method. So, these two are the major advantages of Venner methods. Coming to the disadvantages, hope you know the electrodes have to be moved for each and every measurement. We will come to know of the advantages and disadvantages little later also towards this lecture, right. The disadvantage is, what is the condition for Venner configuration? In Venner configuration, the electrodes have to be kept at equal distance. Suppose if this is the ground surface, all the 4 electrodes are kept at same distance, right. So, the vertical lines are the electrodes, right, and these 4 electrodes have to be at the same distance. The distance between them is A. Hence, if you want to repeat a measurement for a different distance, it is necessary to move all the 4 electrodes. And this method is sensitive to some shallow variations, right. If beneath the surface at shallow depth, if there are lot of heterogeneity, this measurement will be very sensitive to that. And when you want to investigate greater depths beneath the surface of the earth, we may need to use very long cables. Why, we will understand little later, right, because the depth of investigation is proportionate to the distance between the electrodes. If you keep the electrodes at greater distance, depth of penetration will be more. So, when you want to understand something that is at greater depth, then we need to use long lengthy cables, long and lengthy cables. Then the next method is Schlumberger method. What is Schlumberger method? In Schlumberger method, the electrodes are arranged in this fashion, that is, this is A and B, and the inner electrodes are kept much closer to each other, right. That is Schlumberger arrangement. What are the advantage due to this? Major advantage is we need to make some movements alone. That means you need not shift all the 4 electrodes for different measurements. So, fewer electrode movements will be sufficient for every measurement. Then, since we are going to keep these M and N electrodes very close to each other, shorter potential electrode cables are sufficient, right. That is one of the advantage, that is the second one. So, it is sufficient to have shorter potential electrode cables. Then on the other side, what are all the disadvantages? So, these are the disadvantages. One is, it is little bit confusing to carry out Schlumberger method in the field, especially when A and B distance is much more. It is little difficult to understand whether we have kept at the corresponding distance on either side of the electrode spread, right. Then we need a sophisticated instrument, right, to carry out Schlumberger method. Then third disadvantage here is, here too we need large, especially current electrode cables. In the previous case, all the 4 cables have to be longer, whereas here at least 2 cables need to be longer, since A and B will be moved to greater distance. So, you need to have much longer current electrode cables. Then the third electrode arrangement is dipole-dipole arrangement. What is dipole-dipole arrangement? In dipole-dipole arrangement, A and B are kept as a pair somewhere and M and N are kept at some distance, right. This is the ground surface. This arrangement is known as dipole-dipole arrangement. So, dipole-dipole arrangement is of greater advantage, especially cables can be shorter for deeper soundings, right. These 2 pairs will be kept at a closer distance, hence the distance between the 2 electrodes, that is A and B electrode and M and electrode, M and N electrode is very less, due to which shorter cables itself will be sufficient. Coming to the disadvantage side, when we are using dipole-dipole, it is necessary to send large amount of currents. So, it requires large currents. What do we mean by that? Which means we need a high power battery, right, for conducting dipole-dipole resistivity survey. And this method also requires a sensitive equipment. So, this table has given us an idea of about the advantages as well as disadvantages of 3 important electrode configurations that are often used in electrical resistivity investigation. Right. Now, let us quickly again run through the different methods very briefly, different electrode arrangement methods. Before that, let us also look into what are all the merits and demerits. In the previous page itself we had seen, but here I have written in the form of a sentence, right. What is Wenner method? Distance between the electrodes are same. What is the major advantage? Easy mathematics, that is K value, electrode constant is equivalent to 2 pi A, we had seen in the previous slide. However, carrying out this work in the field will be sometimes confusing, because when you want to make fresher and newer measurements, all the 4 electrodes have to be shifted. Whereas in Schlumberger, potential electrode distance is much smaller, so it is easy to deploy, follow in the field. Because what is the difference, right? The potential electrodes are closer to each other, current electrodes are far away, but for every measurement you need not disturb the potential electrode, because according to Schlumberger arrangement, AB should be greater than 3 times of Mn. We say greater than, so it can be here, then you can shift the A and B here, A and B here. So, we can continuously take without moving the potential electrodes at the center. That is one of the advantage. In dipole-dipole, we had already seen, right, these pairs are separated by each other at a very large distance, right. This is applicable for deeper investigations, even up we can try to understand even up to a kilometer by dipole-dipole arrangement. First, we had seen the 3 different methods of electrode arrangement. We have seen their advantages and disadvantages. Now, let us focus our attention to what will be the general depth of investigation as well as area of investigation beneath the profile along which we are arranging the electrode. Depth of investigation depend on the spacing between the electrodes. Here are 2 pictures. In the first picture, the distance between the electrodes are only 10 meters, especially the current electrodes. Distance between A and B electrode is 10 meters. In the second case, distance between the electrodes is 50 meters. So, look at the diagram. So, here we are assuming certain resistivity for this layer, right. for over such a layer of some resistivity, if you carry out electrical sounding, right, by keeping A and B electrode at a distance of 10 meters, the depth of penetration is only up to this. When you increase the electrode spacing, depth of investigation also increase. So, what is very clear is when you keep moving the electrodes to greater distance, depth of penetration also will increase. That is, here is the ground surface, right. In the ground surface, these are the potential. Let us imagine we are doing Schlumberger method. This is A and B. I have taken one measurement. Then I am moving A and B to this location. So, when I move A and B further and further, depth of penetration is going to increase, as you see in this picture, right. When it is only 10 meters, depth of penetration is this. Distance between the two electrodes are increasing. You can see the current goes to greater depth. So, it is related to the electrode spacing. Then depth of current penetration is high whenever we have lower layer is of having low resistivity, right. Depth of penetration is high when the lower layer resistivity is low. This is also very clear because the depth of penetration is also related to the resistivity of the subsurface formations. For example, beneath the surface, if you have clay layer, right, we had discussed already, clay layer is having higher porosity, due to which it is expected to have some amount of moisture. So, just beneath the surface everywhere, if you have clay up to, let us say, up to 5 meters, whatever is the distance which you keep between the electrodes, the current will not go to the second layer at all, because first layer itself is a good conductor. So, current will not be able to go to greater depths, right. So, though here in this diagram we have seen the difference between the same layer, right, we are considering the same layer here. So, when you consider the same layer, certainly as you increase the electrode spacing, depth of penetration will increase, whereas it also depends on the resistivity of the layers at the bottom. Similarly, depth of penetration is low when the lower layers resistivity is very high. That is what I was explaining, right. This is the ground surface, we have clay at the top, whereas lower layer is of let us say sand. So, compared to clay and sand, clay is having low resistivity. This is layer 1, this is layer 2. So, layer 1 is having lower resistivity compared to layer 2. Even in this case, current penetration will be restricted only to the layer 1, right. The difference we had seen in the previous sentence. In the previous case, sand is here, then clay is here. In that case, depth of penetration will be more, because current will tend to go to greater depth, because at greater depth you have a very conducting layer. So, thus though we are saying depth of penetration is related to the spacing between the electrodes, as seen in the second and third bullet point, it also depends on the resistivity contrast between the different layers present below the surface of the earth. Then, suppose if the spacing between the electrodes are very less, right, what we are going to determine? We are going to determine resistance. Resistance is going to be converted to resistivity. Imagine we are doing Venner survey, right. The distance between the electrodes is just 1 meter, which means A is equal to 1 meter. When A is equal to 1 meter, rho A is equal to resistance measured multiplied by 2 pi A, isn't it? So, we had seen already, right, where I am just writing instead of K, I am writing this is nothing but K, right. So, when A value is just 1 meter, That means that is what I am writing here, right. When electrode spacing is very less, the apparent resistivity which we have calculated is more or less equivalent to the true resistivity of the topmost formation. Is that clear, right? For example, if I draw here, this is the ground surface, distance between the electrodes are very close, just 1 meter, right. We have got some resistance and we have determined the rho A value as per this relation, right. Let us imagine rho A value is about 0.21 ohm meter, right. Though it is apparent resistivity, this is almost equivalent to the true resistivity of the topmost layer. Why do we say like this? How do we say like this? This is because of the fact, since we have kept the electrodes at a shorter spacing compared to the depth of the layers, right. Imagine the first layer itself is of about 20 meters thickness. We are pretty sure the current has passed only through the topmost layer, isn't it? So, though we have calculated apparent resistivity, the apparent resistivity will be much closer to the true resistivity of the top layer. Okay. Then, suppose if you increase the electrode spacing, right. Now we had kept at 1 meter. In the diagram you can see two pictures. In first case on the left hand side 10 meters, here 50 meters, right. So, as you increase the electrode spacing, current tend to pass through greater depths, right. So, the value of apparent resistivity which we are getting will keep changing, apparent resistivity will keep changing. Imagine there are number of layers. When you have many number of layers beneath the surface of the earth, that is, this is surface of the earth, right, and beneath that you have the first discontinuity, this is layer 1, layer 2, layer 3. Now, previously we said when the electrode spacing is very close, current was penetrating only in flowing only in layer 1. So, the apparent resistivity which we have got is almost equivalent to the true resistivity. Whereas, in this case now electrode spacing is 50 meters, due to which current is passing through the first layer, then into the second, then into the third. So, what we are going to measure is the combined effect of all the 3 layers. So, the apparent resistivity which we measure cannot be equivalent to the true resistivity of the formation, right. But one thing is clear, as you increase the spacing between the electrode, depth of penetration will increase until otherwise no surprising resistivity values exist in the layers, right. Do you understand? That means whatever I said is also applicable, right. Suppose if you have a very high resistive layer at the top surface, current will not pass through at all, whatever is the distance. Similarly, if you have a very conductive layer, top 5 meter is only clay, even if you keep the electrodes at 100 meters, current will be flowing only in the top layer. So, we have to be cautious about this too, right. So, what happens when the distance increases? Apparent resistivity never reaches the resistivity of the lower layer, because some current always pass through the upper layer. This is what I said. Now, let us imagine, look at this diagram here, right. The current, part of the current passes through the first layer, partly into the second, part of the current passes through the third. Again it passes from here, it passes to 1, then 3, 2, 1 and reaches the electrode. So, apparent resistivity never be equivalent to the true resistivities of the layers found at greater depth, right. This is in contrast with what we had discussed previously. That means, previously I said if the electrode spacing is very less and thickness of the layer is much, first layer itself is comparatively higher, then whatever apparent resistivity which we are measuring will be the same as that or almost same as that of the true resistivity of the top layer. Whereas in this case, the apparent resistivity which we are going to measure for a electrode distance of 50 meters will not be equivalent to the true resistivity of the lowermost layer. Why? Because there are couple of other layers above that, the current actually passes through all of them. So, we get the combined effect of all these three layers. Right. Then changes in apparent resistivity with electrode spacing depend on depth to the interface and the contrast in resistivity. This we had almost discussed. So, what we mean here is the apparent resistivity which we are going to get for this configuration, the apparent resistivity which we are going to get, let us say when the electrode spacing is 75 meters A and B and Mn is somewhere here, let us say we are doing Schlumberger method. So, the apparent resistivity which we have got in previously we kept at 10, at 50, now we are keeping the electrodes at 75 meters. So, when you keep the electrodes at this distance, the apparent resistivity which we measure is depend on depth of penetration of current as well as the resistivity, true resistivity difference between the layers. This is layer 1, layer 2, layer 3. Okay. So, the value which we get depend on obviously the spacing and also the contrast between the true resistivities of the layers present below the surface. Generally, as a rule of thumb, we can assume depth of penetration is A in the case of Wenner method, right. Suppose if this is A is equal to 5 meters, generally we can assume depth of penetration is 5 meters. This is 5 meters. Okay. Suppose if we are using Schlumberger method, then depth of penetration is half of the distance between A and B. So, we do not worry about the distance between M and N. So, suppose if the electrodes are arranged like this and the distance between A and B is let us say 100 meters, what will be the depth of penetration of current? It is only half of AB. So, depth of penetration now will be 50 meters. Okay. Then the apparent resistivity value which we obtain for this configuration is pertaining to which location? Always it is pertaining to the center of the electrode spread, which means when the electrodes are kept at 10, you look at this diagram here, right. If the electrodes are kept at 10 meter apart, we are measuring the resistivity at the center point. Okay. So, when you keep the electrode, I will go back to Wenner. This is Wenner arrangement. Now, we are investigating the subsurface at this location. Okay. That means what is this location? This is the center of the electrode spread. Right. Now, imagine the distance between the electrodes is 5 meters. 5, here is 5, here is 5, which means the apparent resistivity value which we are getting is from a point which is located at a depth of 5 meters. Is that clear? So, now we have understood what is the relation between the contrast in resistivity values of different layers below the surface and what is the relation between the apparent resistivity which we are going to measure and the distance between the electrodes. Thirdly, we had also seen what is the point of our investigation. The point of our investigation is the location of our investigation is the center point of the electrode spread. So, 3 things we have learned. Then the next is when you conduct a survey, what is the cross sectional area which we are investigating? That is the next thing. So, what is the area which we are investigating? So, this company has given us a nice diagram, right. So, what is that? Suppose these are the locations of electrodes, whether it is Schlumberger or Wenner. Let us assume we are doing Schlumberger survey. This is A, B, M, N. This is the center point. So, we are investigating this particular point now. Okay. So, that is what, this is the point of our first investigation, station 1. Though the current passes through in different ways as I am drawing, our station location is 1 and the depth of penetration now is, suppose if you are using Wenner method, what is the depth of penetration? AB by 2. Imagine the A to B distance is 100 meters. Now, this point will be at what distance? It will be at 50 meters, because we know depth of penetration is approximate, right. Approximately it is AB by 2. So, for this center point, we have got a value of apparent resistivity from a depth of about 50 meters, which means we have investigated only this triangle, approximately only this triangle has been investigated by us. Suppose if you want to investigate more area, what we are doing is we are just shifting the electrodes. This was the station 1, we need to have investigation carried out at number of stations. So, now this is the next station. When you carry out survey in the next station, the current goes up to this, right, same electrode spacing. That means this was initially 100, right. Now, for the new station 2, the next line of investigation is also 100. So, here too we are getting a information at this place, which means as you move the electrodes toward this direction, you are continuously studying this area. Okay. So, area of investigation is a triangle beneath the two outermost electrodes. So, we have understood what is the relation between distance between the electrodes and depth of investigation. Now, we have understood what is the area of investigation during the resistivity survey.